Here I want to go through oxidation states, oxidation numbers. So typically, most people will start by presenting oxidation states with a set of rules. And it looks something like this, maybe they're a little longer. But they'll say fluorine is -1 in its oxidation state all the time unless it's monoatomic or diatomic. Hydrogen is +1 unless it's by itself or if it's with a metal. Oxygen is -2, and the number of exceptions grow, and then eventually they tie in that everything else has to make the total add to 0. I think this is the wrong way to introduce this, and this really should be kind of taught as a consequence of what an oxidation state is. Instead of that, what we really should be doing is we should be going through and trying to create an image that oxidation states are artificial. They're something that scientists made up. They're something that we made up, and they serve a purpose. And what is that purpose, and why do we do that? Oxidation states are defined by how atoms share electrons. Okay, but they're defined from our perspective. And so we've actually set up a rule that says this. If two things are bonded, and they each have their own electrons, that for oxidation states, or oxidation numbers, we're going to look at what the charge would be if we were to assign these electrons that are being shared between the two both to one of those elements. And so the correct way to teach oxidation states is to compare and contrast it with formal charge. So in oxidation states, oxidation numbers, both of those electrons both go to the more electronegative. So let's assume that B is more electronegative than A. Then when we count electrons and protons around both A and B, we would say that the B has these two electrons, and A has just whatever electrons are in its core and in its valence shell. Not with those two. In formal charge, it's a very, very similar process with a slight change in the rules. In formal charge, this is I like to say it's kind of everybody gets a trophy day. No matter who is more electronegative, we assume that those two electrons are split down the middle, and one goes to A and one goes to B. Now that can be the same for oxidation numbers in the event that A and B are the same. So if we have a diatomic, then we will split them as a tie. But oxidation numbers is more of your winners and losers, and formal charge is more of your everybody wins, hooray. Okay. Now, the distinction for oxidation numbers is which one is more electronegative. Okay. So then the question is, well, what's the most electronegative thing? Okay. And then what exceptions will that have? And so fluorine, we all know, is the most electronegative element. So if I bond fluorine to anything, then fluorine is going to win that battle of electronegativity. So from our perspective that we're assigning, fluorine will get those two electrons, which will give fluorine, which will have its 6 other valence electrons. It'll give it a total of 10 electrons, or 8 valence. And so it'll give it a -1 oxidation number every single time. The only exception to that is if you happen to bond fluorine to fluorine, which is also as electronegative, in which case you get a tie, and they would then split evenly and you get an oxidation state of 0. Nothing else has the electronegativity of fluorine. Okay. Well, what else is something that has a very consistent electronegativity? Well, hydrogen. Hydrogen is more electronegative than every metal and less electronegative than every non-metal. And so if hydrogen is paired up with a non-metal, it'll be +1, and if it's paired up with a metal, it'll be -1. And if it's paired up with itself, it'll be 0. So we assign fluorine first, then we go through a hydrogen, and then oxygen is your second most electronegative. So oxygen will be -2 unless it's bonded to itself somehow, which there are many ways to do, or if it's bonded to fluorine. Okay, and so as we deviate from the most or least electronegative, we get more of these exceptions. Okay, alkali metals and alkaline metals are the lowest electronegativities, so they will always be +1 or +2, and so aluminum will probably always be +3, with rare exceptions. Now, what we should be doing is we should be going through and looking at this from a structural perspective. So what I've done is I've put together 5 examples that I think kind of highlight the key ideas behind oxidation numbers, and then can feed into the purpose behind oxidation numbers. Because keep in mind, this is not something that exists in real life. Elements and atoms don't have oxidation states. I'm assigning them based on this arbitrary kind of means. So why would I do that? Okay, so if we go through and look at HF, the way to assign the oxidation states on HF would be to say, well, which one is more electronegative? Okay, and that's the fluorine. So the fluorine then is going to get all of those electrons. So that's 8 for the fluorine. It has 2 core, that's 10 electrons, only has 9 protons. We give it a -1. Hydrogen has 0 electrons total and 1 proton, so it gets a +1 oxidation. Now, if we were to look at that from a formal charge perspective, same molecule, we get a different answer. Because in formal charge, it doesn't matter that fluorine is more electronegative. All that matters is that we split these evenly. So in that case, hydrogen gets 1, fluorine gets 1. That gives fluorine 7 valence, 9 total. So it has a formal charge of 0. And hydrogen gets 1 electron, and that would also have a formal charge of 0. So both of these are systems of tracking where the electrons are, but they serve different purposes, and therefore we end up with 2 different results. Right? Now that's a pretty simple example. Let's go ahead and look at a different one. Let's look at number 3 here, hydrogen peroxide. Okay? Peroxides are one of those exceptions. Well, why is that an exception? Okay? Well, if we look at the structure, it becomes kind of clear. When I look at this, the oxygens are bonded to each other with one of their bonds. So with regards to oxidation states, we have a winning and losing battle here. The oxygen is going to get those. But there's going to be a tie that occurs here. Okay? So that tie is going to cause the oxygen to get these 2, 1 more, 3, 4, 5, 6, 7 electrons at its valence, 9 total, compared to 8 protons, and so therefore this gets a -1 oxidation state, this one also. And then the hydrogens both have no electrons in this system. Okay? If we went through into formal charge, everything would have been split evenly. So this would have been split evenly, this would have been split evenly, and everything would have had a formal charge of 0. Okay? Now, this whole redefining the way that we look at oxidation states came about because of number 4. And this is a really critical one. So C3H8, if we go through and we write out the formula like this, and we say, what are the oxidation states? You would decide hydrogen first, and it would be a +1. And there are 8 of those +1s, which is a total of +8 oxidation numbers. So that means that carbon needs to add up to -8 in order for this to function. But there are 3 carbon atoms, so how is that split up? Well, if we take -8 and divide it by 3, we get -8/3, or -2 2/3, we get a fractional component, and that doesn't really make sense. So, if we look at the structure, we can see how we could get such an odd oxidation state. So here's propane. We're going to analyze this from an oxidation number perspective. Okay? So carbon and carbon tie, they would split. Carbon and carbon tie, they would split. But then carbon would win all of the battles. Okay? So the carbon that's here is actually different than these 2 with reference to oxidation states. This one has 2, 4, 6, 7 electrons. Okay? This one, though, only has 2, 4, 5, 6. And this one has 2, 3, 5, 7 electrons. So with the 7 or 6 or 7 valence electrons we've assigned to them, which would be 9, 8, 9 total, this carbon is coming out with a -3 oxidation state. This one has a -2 oxidation state, and this one has a -3. Now, when we get into organic chemistry or something, this carbon being different might become relevant. So we want to look at this from a structural perspective, but we want to look at this from assigning it via electronegativity values. And that sets us up for a purpose later, and the purpose of this is to look at what's happening to this chemical as time goes by, and are electrons leaving it. So our assigning of oxidation numbers is really so that we can go through and take a look at an equation. So maybe we have something like this, where we react iron 2 with permanganate and acid, and it turns into water, and then 2 plus, and iron 3. Well, that's a very complex looking equation, but with oxidation states, what I can do is I can have assigned where all these electrons are, and then I can go through at the end and say, okay, well, this thing, is going from a +2 to a +3 oxidation state, therefore it's losing electrons. And the manganese, specifically the manganese, is going from a +7 to a +2, therefore it's gaining electrons. And I can then, do some engineering there to take advantage of the fact that I can move electrons from from one nucleus to another, and I can intercept that and create electricity. Okay, so oxidation states have a purpose of looking at where electrons are and where they are not. But when we go through and treat it as rules, we introduce the notion that we're looking at something that's systematic, something that's natural, something that actually is a thing. And it's not. It's a very artificial, scientist-constructed system that serves the purpose of analyzing something involving a redox reaction. Okay? And of course, we typically start with naming and formula writing with it, and that reinforces that misconception. And so what we really should do is we should go through and look at structures first and say, who is the winner, who is the loser? Now, I said at the beginning that one of the key things here that we can do with this is we can contrast it with formal charge. So the last example on here is carbonate. And so I like formal charge as a connection because formal charge goes through and it says, you know, what's the best Lewis structure? When is my octet being met? When do I have a lot of charge on a very electronegative atom? And it has its own separate purpose, but the mechanism to get it is very similar. So in formal charge, everything gets cut in half. 2 electrons here, 2 electrons here, 1 electron here, 1 electron there, 1 electron here, 1 electron there. And then we total that up. That carbon has 4 electrons assigned to it in the formal charge system. 4 valence, okay? And the oxygen has 7 valence electrons. And this oxygen has 7 valence electrons, and this one has 6. So for formal charge, I have a -1, a -1, a 0, and a 0. Okay, and the total of that is -2, which we would expect because carbonate has a 2- charge. And the formal charges and the oxidation states will always add up to the total charge. But if instead I were to look at this from an oxidation state perspective, then it would be very different. The carbon would lose every single battle because it's less electronegative than all the surrounding oxygens. Now this oxygen has 8 electrons. This one has 8 electrons, and this one has also 8 electrons. Carbon has 0. So, according to oxidation states, every single one of my oxygens has a -2 formal charge. It has 8 valence compared to 6 valence that it would normally have. It has 10 electrons instead of 8. It has an additional 2 compared to its protons. And on this particular case, the carbon only has its 2 core electrons, it's missing 4 electrons, has a +4 oxidation state. And then if we add up +4 plus -2 plus -2 plus -2, of course it adds up to the 2- charge. So the distinction between formal charge and oxidation states is very clear that it's 2 different systems. One's used to kind of show how a Lewis structure looks, the other's used to track where electrons are. But the mechanism by which you approach them are both artificial, and they're both so similar, and they're both arbitrarily decided that we would split evenly or not. And so the connection between them is really, really important to giving a really good concept that you could then go through and understand the purpose of. Okay? Now at this point, if we go back to our rules, now our rules all make sense. Why is fluorine -1? Well, because it's the most electronegative. So the only time that won't occur is when it's bonded to itself. Why is hydrogen +1? Well, because it's kind of in that gap between metals and nonmetals. And so if it's bonded to a nonmetal, it'll be +1. If it's bonded to a metal, it'll be -1. If it's bonded to itself, it's 0. Why does oxygen have a few more exceptions? Well, because now fluorine is more electronegative than it, and it can bond to itself in numerous situations, superoxides, peroxides, or just diatomics. Why are alkaline metals on here? Well, because they're the least electronegative. Okay. And then at the end we use the rest to make the total add up to 0, assuming that everything else is in between those extremes. Okay, so that's how oxidation numbers work, and that's really the purpose behind what we're doing is we're trying to get you to understand that later we're going to move electrons around on purpose from elements to other elements, and we're going to try and intercept that as electricity. And we want to lay the groundwork for the concept of how we assign electrons and how we've chosen to assign electrons in oxidation numbers.